share the screen. Yeah, right. So now the screen is visible. Hello?
Yes, sir.
Okay, good. Yeah, okay. So welcome to the class. Anyway, today we have again we have a quiz as usual at 11:40, and this quiz will be about 15 minutes, 11:40 to 55. Okay, and we'll stop the lecture at 11:35, and you can take the quiz. Okay, yeah, and and in continuation to the last lecture, so in the last lecture we just introduced the concept of threads with respect to the processes. So we discussed about the basic distinction between the definition of a process and a thread, right? So, and we also analyzed, discussed with respect to the examples, quite a few examples of a multi-threaded process. It means a process having a single thread. It's a normal process by definition. And a process having a multiple executions or multiple threads of execution, it's known to be a multi-threaded process and all. So that way, the definition you can, if you want to define the process, means a program in execution known to be a process, because a program means it's it's a sequence of instructions, and if they are in execution, then it's known to be a process. And by default, the process has a single thread of control. It means only one sequence of execution. And whereas coming to the concept of threads means in a process, if you have a multiple sequence of executions, if in a process, if you have multiple sequence of executions which are independent, then you can able to execute the process on a multiple processes simultaneously, on a multiple process simultaneously and all. So therefore, if you want to define a thread, the way the thread will be defined as it's an instant of execution on a CPU, known to be a thread and all. Because a process may have a multiple threads, and given a chance, and if we have a multi-core processor is available or multiple processors are available, then if there are multiple execution sequences are available within a process, then you can able to run these multiple execution sequences on multiple processes simultaneously. So that way, the thread can be defined as it's an instance of execution on a CPU. So that way, you can define a thread, whereas a process is nothing but execution of a program is known to be a process and all. And we have seen in the last class, given an example like a word processor can be viewed as a multi-threaded process, where it can able to handle with the one thread, it can able to handle the user inputs. With another thread, it can able to take care about the display, and other thread maybe for spell check. So likewise, you can have the multiple threads where you can have the multiple activities can take place simultaneously. And so that way, most of the application process, whatever at present, most of them are like they are a multi-threaded process which tries to exploit the efficiency of these multi-core processors and all. Okay, and let us see the one of the examples which we very frequently use. This one, the in a kind of in the context of client server paradigm. So it means that suppose, for example, you are browsing some web server for a particular website. So as a browser, you will be a client, or from your machine you are browsing for certain websites. So you will be a client, and then the web page may be available on certain server. So that server will happens to be a server, and is to be a server which used to provide the desired web page for you and all. So in that case, in case of client server configuration paradigm, where the server used to receive multiple requests from the clients regarding the web pages, because it used to hold the web pages. So therefore, there will be multiple requests from the different clients very frequently. So in that case, if the server has a single process or single execution sequence contains a server process contains, if you assume that it's a single execution sequence, so in that case, to handle this multiple requests, it takes a lot of time. That means there should be these client requests will be pending for a long time because there are multiple requests used to be there. Because lots of clients want to access the web server, and assume that if the server is a process having a single thread of control, so in that case, the process will first take a first request from a client and it used to process. And once it is completed, then only it can able to handle the next request. So likewise, if the server is a process of single thread of control, then it takes a lot of time to handle the clients. And so to take care of that, the one earlier solution used to be like the server used to create a child process. It is exact replica of the same child process. So with that, whenever a client request arrives, then the server will create a new process known to be child process. And the child process is exactly the same way of the server, as we know that it generates a duplicate process, and the child process will handle the client request and the server will be looking for a client request and all. So therefore, whenever the new request arrives, then the server create a child process and the child process will be assigned to the client request. Then the child process will perform the job. So that way, earlier, before the concept of threads and all, the server process used to create a child process, and the child process are used for serving the client request, the multiple client requests and all. But as we know that creating a child process is a heavy process. It means that with respect to the point of resources, like whatever the server process is there, the same amount of memory is required, and whatever the files the server process are using, all the files are required even for the child process also. So therefore, it needs a lot of resources and all. And so that way you can say that it's a bit involved in creating a child process and using a child process for serving the client requests and all. So whereas the other way is that using, suppose in case if the server process is a multi-threaded one, if a server process is a multi-threaded one, so in that case where it can able to handle the client request using the separate threads. That means suppose when a client arrives, when a client request arrives, then the server will create a thread, and then that created thread can be given will be the whatever the client request is there, that request will be passed to the newly created thread, and the server will again keep on listening to the request with the other thread. So likewise, whenever the client request arrives, instead of creating a process, the server can able to create a thread, and that thread can be allotted to the client request, so that the thread can able to take care about it can respond to the client request and all. So the difference between these two, the creating a thread versus creating a process, as we have seen in the last class. So creating a thread means actually it's not much involved, because the threads is nothing but it's from the within a process. So therefore, whatever the process resources are there, like a code segment, data segment, and other the files that are provided by the OS and all, so they will simply share that one. It's not taking the replica, it's not taking a copy of that. Whereas in case of a child process and all, it will make a copy of all those things. So therefore, you need to have separate memory space is required, and then all these resources are like the multiple copies are required. Whereas in here, in case of multiple threading or threads, where it will not create a copy and all, it just share the resources of a process. It means that whatever the code segment is there, and for all threads and all, it just provide the pointers to the code segment, and then those threads will run parallelly. So that way there is not much the additional resources that are not required in case of a threading and all. So therefore, the multiple threads or the multi-threaded process is more advantageous compared to having the multiple processes and all. That means instead of generating a child process for handling a client request, so here in this scenario, if the server can create a threads, the new threads as and when the request arrives, then it will be much easier and much efficient way of handling the request and all. And yeah, this one we have seen. So this is just to illustrate that how the single and multi-threaded process will be like sharing the resources and all. And here in this, there are two, like in this figure, you can say that the figure in the left side is to illustrate a process having a single thread. It means that only single execution sequence. So for that, anyway, since the process, we have this code segment, data segment, files provided by the operating systems and so on. And then to run the process, here the register CPU register set is required, separate CPU register set is required, and then along with that, a separate the memory space that is required to take care about the local operations, or like local variables and function calls and other things. The stack is required and all. So therefore, this is the you can able to see that the process with a single thread of control, that what we have seen in the like in the third chapter and all, like when you're discussing about a process, the way the environment will be something look like this. Whereas if it is a multi-threaded process, and here the illustration we have given, the process contain the three execution sequences, three threads, and for all these three threads will share the same code segment, data segment, and the operating system files, whichever is shared by the operating system to a process. All these three threads will share this common data and all, like a code segment, data, and the files, whatever it is. And since there are three separate execution sequences are available, so therefore to run these execution sequences, you need to have the specific environment is required. For running this particular thread and all, you need to have its specific stack and specific registration set of registers are required for its execution. Likewise, for each thread, it requires that one. So therefore, in case of multi-threaded process, the thread specific resources are like needs a specific stack and needs the specific register set is required to maintain the its environment and all. And whereas remaining all resources are will be shared by these threads and all. So that way you can say this the multi-threaded process and a single-threaded process. These things are common, like a code, data segment, and all files are common. The only thing that are like additional ones are there. As per the number of sequences, number of threads, it requires that many sets of these specific environments are required, like specific stack and specific registration set is required. So because it's obvious that intuitive also, because here now the process, you can able to run the process on the three processes simultaneously if it is available. So if these process will run on the three processes simultaneously, so to track these execution sequences or execution environments, you need to have the separate stack and separate register set is required and all. So that way, this is the way you can able to view the multi-threaded process compared to the single-threaded process. And yeah, now we'll look at some benefits of multi-threaded process, which are obvious. By this time, you will be aware of that. And when you go through this, it will be, you can feel that. The responsiveness, so it means that, suppose, for example, you have a single-threaded process, and where the single-threaded process, when the execution is going on, and if the process is blocked, if the execution was blocked because of the IO, then the entire process will be blocked. That means the process will be switched and the new process will be handled by the CPU and all. Whereas if it is a multi-threaded process, then if one of the thread was blocked because of the IO or whatever, then the CPU can be allocated to the next thread, some other thread. So likewise, you can, since if it is a multi-threaded process, you can switch the threads among within the process, so that the thread or the execution will not be blocked with respect to the specific IO and so on. And not only that, actually this responsiveness is with reference to particularly the interactive applications. Suppose, for example, you have an interactive application, and if you design that application process using a single-threaded process, then it is very difficult to maintain that interactiveness, because the process may have some execution sequence. At certain point of a time, a process may be involved with a highly computational execution. So in that case, you have a sequence of the computational instructions used to be there. And at that time, if the user want to interact with the process will not respond at all, because the process has only one sequence of execution. And now at this particular point of a time, now the process is executing with a particular computational code. So where it has a lot of instructions, it will go one by one and all. It will not respond to the user inputs and all. Suppose if you design the process as a multi-threaded process, so in that case, you can able to design the process as a multiple threads, and where a specific thread can be allocated for the user interaction and all. So that way, even though a particular thread is running and it's computational, and you can able to, there is another thread which is will be used meant for taking the user inputs. So that way, it will appears like a more interactive compared to the single threaded process and all. So that way, the responsiveness means that one. If you have a single thread of process, the process may be blocked because of the inputs or because of some other thing. Whereas if it is a multi-threaded process and all, you can switch the threads even though one of the thread was blocked. And another thing is that you can for more interactive applications and all, the like multi-threaded process will be more advantageous or more beneficial and all, because a specific thread can be devoted for user interaction, so that always that particular thread will be like used to accept the user requests and all. And then the resource sharing. And here, as we know that in case of threads, as I already mentioned, that here the resource sharing is very simpler in case of a multi-threaded process, because you have multiple threads and all these threads are part of a process. So therefore, whatever the process resources are there, like a code segment, data segment, and so on. So all these things can able to freely access those resources and all. Whereas in case of a normal process, if you want to share the resources and all, it has to use the concepts like a shared memory or message passing schemes has to be used, which are defined by the user, and it requires a lot of involvement of the operating system, and the user design is also required and all. Whereas in case of threads and all, you can able to communicate from the process and all in a very direct way, because the threads are part of a process and also they can able to communicate, they can able to share very effectively compared to the process and all. And then economy. The economy means in the sense that like management of a process with respect to the management of threads. Like for example, if you take, as I mentioned, a web server and all, if you want to manage the web server effectively, if you don't assume that a concept of threading is not there, then what you need to do for every client request, you need to create a child process. So that way you can have several child process will be created, and all these child process used to manage the client requests and all. And compared to that, if the process is a multi-threaded process, it means that whenever a request arrives, you can create a thread, and that thread can be used to handle the request. So compared to the multi-process, multi-threading will be advantageous, because the creation of a thread will be much easier or simpler compared to the creation of a process and all. So there are some statistics in case of from Unix or Solaris systems. Creation of a thread is almost like a 30 times approximately faster than the creation of a process and all, right? And context switching is also much easier in case of a threading compared to the process and all. Like it is faster, much faster compared to the process. So that way here the economy means you need to take that in that particular sense. Yeah. Yeah, what happened? Hello? Hello? Hello?
Yes, I am
Hello?
audible.
Hello? Yeah, is it
Hello?
audible now? Yeah, yeah, I
Yes,
think somewhere I got some warning. That's why I'm just stopped here. Is it now clear? Now is it audible?
yes, sir.
Yeah, yeah. Can you see the screen, or still screen is not available? You're not able to see? Screen means what I mean to say, the slide.
Yes,
Yes,
sir.
sir.
Yes.
Slide, sir.
Yeah, yeah, you can see the slide. No, okay, fine, good. Yeah, yeah, we are discussing about economy. Economy means basically like creation of a thread, managing the thread, and so these things will go under the economy. The advantage related to the economy of using multi-threads, multiple threads compared to the multiple process. And the scalability is this is nothing but, suppose you have a process having a multiple threads, you can take advantage of multi-core systems or a multi-processor systems and all. So if you have a process having multiple threads, you can run those threads parallelly by allotting them or by scheduling them onto a multiple process and all. Yeah. Right. Okay. Uh, yeah. Okay. So that's what mean by scalability. It means that the same process you can able to run parallelly on a multiple cores. Right. So that is what mean by the scalability and all. And otherwise, even though if your process is a single thread of control or a single execution sequence is there, in that case, even though you have multi-core systems or multi-process systems, you cannot take that advantage of that because you have only one sequence of execution. So therefore, all the instructions has to be run in a serial way. So you cannot take the advantage of this availability of multi-core systems. So that way, these are the a few benefits of multi-thread concept of multi-threading. And then the multi-core programming means here the idea here since we have a multiple threads, it means that a process can able to run on a multiple process if they are available. So that way, the people now, if you want to take the advantage of that, so therefore, they initially, if you want to have a more effective, uh, like more effective way of utilizing the system and all. So in the software, you can have multiple threads in a program, so that the program can able to run faster. That means you can, if the multiple processors are available, you can execute the program, a same program or the same process on a multiple process simultaneously, so that it can execute much faster compared to the on a single process and all. But actually for doing that, that means a process, or you can say that the program should be in a multi-threaded fashion. That means the program has to be designed, or the program has to be written, or program has to be available in a way that it should be in a multi-threaded fashion. So for doing that, actually here, because of these, to create a process to be multi-threaded process, like the application programmers will need to face the following challenges. It means that the earlier, actually, if you have a program, means then you can able to write, if you have some task or some application, without bothering about the multi-threading. So you just think about the solution and you can able to write the code for that, where it can able to run with a single thread of control. And since because at that time you have only in a system only one processor is available, so therefore single thread of control is good enough. And whereas now with the availability of multi-core systems or multi-processor systems, where if you want to take the advantage of that, if you want to execute in an effective way, where you can able to write the program in a multi-threaded fashion, or if you try to introduce the program in with a multiple execution sequences which are independent to each other, then you can able to utilize the advantage of the multiple cores or multiple process and all. So in that process, for designing the program to be a multi-threaded process, a multi-threaded program, so these are some of the issues where the application programmer has to be taken care of. So first one is the dividing the activities. Suppose we have an application program, and if you want to design that program to be a multi-threaded program or a multi-threaded process, so there you need to identify, that means the user or the application programmer has to be identified the multiple tasks or multiple subtasks that are involved in the overall program or overall task and all. And he has to identify those activities or the tasks should be independent of each other, so that he can able to provide the threads, separate threads on each of these sequence of instructions, so that he can able to run them parallelly and all. So therefore, identifying the activities which are independent within a process has to be carried out first. So therefore, it means that you need to divide the activities of the overall program into the multiple activities, and which are to be as far as possible to be independent to each other. And so that is one of the tasks where the application programmer has to be worried about if you want to write a multi-threaded program. And the second one is the balance. That means after identifying the activities or the subtasks in a bigger program, in a normal program, and these subtasks should be balanced. Balanced means in the sense that all the activities or all the subprograms or the subtasks, that whatever you identified, they should be more or less perform the equal job. So therefore, it means that whatever the activities you are identifying, so they should be balanced. That means all of them should be more or less has to be take equal amount of time or equal value has to be given as output. And the data splitting. So the data splitting means suppose you are running a program on a database where the database contain a huge amount of data, like you have lots of records were there and you need to perform certain operations on that. So where in case of multi-threaded concept where you can exploit that, suppose you have a huge amount of data, like for example, you have, for example, some 10,000 items or 1 lakh items are there, and you need to perform some operation on that. That means you need to perform, for example, you need to add certain thing in a particular record. Likewise, we have 1 lakh records were there and all. So like otherwise, suppose we have some array of numbers were there, and you need to perform some operation on that. So in that case, actually, in case of you exploit the data splitting, it means that, for example, you want to perform some sum of an array of numbers, for example, and where that array size is so big, it's very huge. And if you want to exploit, or if you want to use the parallel programming, or if you want to use the multi-threaded programming in that particular context, you can split the data, that depending upon the number of cores and all. Suppose, for example, you have n cores are there, you can split the data, partition the data into the n sub items or n chunks, and you can able to perform the operation on that. Suppose if you want to perform summing operation, so instead of summing the integer items one after another, you can able to split the data into as many number of cores or as many number of processes that are available, and then where each thread or each processor can perform the sum independently. And after performing all these things, the individual sums, you can able to sum up all those things again. So that way you can use the data splitting also idea for in view of multi-threading. And anyway, when you are using the data splitting and when you are handling the data using the multiple threads and all, then you need to be careful about the data dependency and all. Sometimes suppose you have multiple tasks are running, sharing the data. So at that time, you need to have, there will be some data dependency will be there. That means after performing certain tasks, some tasks need the inputs from the other tasks and all. So in that case, there should be some coordination, some synchronization between the tasks are required and all. That's what mean with the data dependency and all. It means that the threads are executing parallelly, and whereas for some with respect to certain tasks and all, some thread need the input from the other threads and all. So at that time, you need to have some kind of coordination or synchronization is required, or a specific thread which needs the input and all, it has to wait till the completion of other threads operation. So that way it's known to be like a kind of data dependency. And finally, when you are creating a multiple threads within a process and all, the testing and debugging is also very, very complex and all. If you have a single thread of control, it means that you have only one path of execution, so that you can able to track what is happening when the instructions are executing one after another by using appropriate simulations and so on. But here in this case, in case of multi-threading concept, where you have several execution sequences are there, or several paths of sequences are there, and there are lots of dependencies also may be there between the paths and all. So in that context, the testing the program correctness of a program, or debugging if there are any errors or if there are any mistakes were there. So it will be very tough or very complex in view of the multi-threaded programming and all. So all these are the various issues where the application programmer has to be worried about when he's designing the program to be the multi-threaded process and all. Okay. So, and then coming to here, in the case of this multi-core programming or a multi-threaded programming, we'll come across these two terms like a parallelism and concurrency. So the parallelism means by this time you will come to know what is the parallelism, because if your process is there and in the process contain the multiple execution sequences, for example, and then if you allow these execution sequences parallelly, simultaneously across the multiple cores, then we say that the process is executing in a parallel sense, because the parallel a process has a multiple execution sequences, and these execution sequences we are running simultaneously. So it's known to be the parallelism. It's known to be concept of parallelism and all. And whereas in case of concurrency means, so concurrency actually supports more than one task. Like earlier, the systems are not the multi-process systems. Earlier, the systems are only the single processor only. But we will support the multiple tasks or multiple programs we are supporting. How we are doing? By using the CPU scheduler. That means by using scheduler, we'll try to provide the CPU to the multiple programs in a very systematic way, in a very scheduled way, so that all programs you can able to see a progress at certain point of a time and all. So that concept is known to be concurrency and all. That means concurrency supports more than one task and making the progress. Even though you have only one processor, or if you see the system, only one process is in execution at any point of a time. But you are scheduling the process to a CPU such a way that the multiple process you can able to see a progress and all. As a user from outside, even though you are running the multiple activities, but still you can able to see a progress across all the activities and all. This is because of concurrency. And whereas the parallelism is nothing but it takes care of both concurrency as well as parallel. It means parallelism is you can able to schedule the multiple execution sequences parallelly across on a multi-core system and all. So therefore, the parallelism you can able to see on a multi-core systems, and whereas the only concurrency you can able to see on a single processor system and all. In a multi-core system you can able to see concurrency as well as parallelism. It means that even though the multiple process you can run on a multi-core system, you can able to see a parallelism as well as the concurrency also, because concurrency means the multiple, if you can able to observe the progress in the multiple jobs or in the multiple tasks, it's known to be concept of concurrency. Because for us as an observer, as a user, you can able to see the several tasks are running parallelly, can able to progressing, right? Whereas a parallelism is true parallelism means that is happens only in the multi-core systems and all, because you have the multiple processes up there where you can able to schedule these things, the same process across the threads, across the multiple cores, so that you can able to see the parallelism in execution and all. So this is the basic difference between the parallelism and concurrency. It's very important, the distinction between the concurrency and parallelism. Observes to be like both sound similar, but the basic difference is that what is the underlying system and all. If the underlying system is a single processor system, it means that it entertains the concurrency. If the underlying system is a multi-processor system or a multi-core system, then it handles both the concurrency as well as the parallelism. Yeah, then coming to the multi-core programming, yeah, these you can able to see the two types of parallelism you can observe, you can able to notice in the case of multi-core systems that we have seen when you are discussing about the various issues where the application program you used to face when you design the multi-threaded process. It's a data parallelism. It's nothing but distributing the subsets of the same data across the multiple cores, performing the same operation. As I mentioned, for example, you want to perform the sum of some array of numbers, and assuming that array is so big, so where you can able to split the array into like subsets, and you can able to perform the summation within the subsets, and after completion of the summation within the subset, then you can able to sum those partial sums and all. So that is the concept of the data parallelism and all. Whereas the task parallelism means, as I already mentioned, in case of multi-threaded process, where you have one application process where you identify that there are some subtasks which you can able to run parallelly. And then if you identify those tasks, then those tasks can be viewed as the independent execution sequences, and you can able to schedule those tasks, subtasks on a multiple process, so that the task can be you can able to see the running the subtask parallelly over the multi-core system and all. So that was the difference between the data parallelism and the task parallelism and all. Data parallelism means the same task will be run, and where the data will be distributed in the across the multiple processes. Whereas in case of task parallelism means the different tasks are scheduled on the different process, and overall the multiple tasks will be executed or can be completed. And then another thing is that in a CPU, on a CPU, at any point of a time, only one execution is possible. Only one instance of execution is possible on a CPU and all. But actually, to improve the performance and all, as the number of threads are increases, threads in the user level increases. So to support that, the hardware experts and all, they designed the multiple multiprocessor architecture so that it supports the user level threads and all. And at the same time, even the single core, let me single CPU, can be designed such a way that it can able to handle the multiple threads. It can able to handle the multiple threads. It's not simultaneous. It is in a concurrent way. Because, for example, you have one CPU was there, and then that CPU will be scheduled to the multiple threads, to a multiple threads. The reason is that, suppose, for example, CPU, when it is executing a particular instruction, suppose a memory level instruction, for example, then it has to load the data from a memory, from a main memory. It takes some time. It takes some 100 nanoseconds or whatever and all. So there, in the meantime, because some memory operation is going on, so in that time the CPU will be idle. Then you can able to schedule the CPU with some other thread. So that way you can able to like the hardware threads means on a single CPU you can able to run the multiple threads in a concurrent way. In a concurrent way. So the example, as I mentioned, that suppose the instruction is a memory-based instruction where it needs to, that means the data has to be arrived from a memory where it needs some amount of time, some 100 nanoseconds or 50 nanoseconds and all. But if the clock rates are at order of 1 nanosecond or less than a nanosecond, so at that time the CPU will be just waiting for the data to be arrived from a memory. So in the other way, that if you can able to schedule the CPU with multiple threads, in the meantime, the CPU can able to perform the job of some other thread. So that way you can able to schedule the multiple threads on a single core. So that way you can see that these Intel CPUs, for example, it supports two threads per core. And whereas some other systems and all, where in case of Spark T4, it contains the 8 cores, basically the processor, and where each core will support 8 hardware threads. It means each core will be scheduled with the 8 threads. So that way you can, so these are not to be hardware threads, and these things we'll try to discuss when you are discussing about the CPU scheduling and all. At that time, we'll just try to give some additional information, additional details we'll discuss about here and all. So software threads are basically the user level threads are nothing but the threads are within a program or within an application program and all. And hardware threads are nothing but on a single CPU, you can schedule the multiple threads. But the CPU can able to execute at any point of a time only one thread it can able to handle. But how it will schedule, how it will entertain the multiple threads? By using the concurrency and all. Like if it requires some memory instruction is to be executed, at that time it takes some amount of time. So in that within that time, the CPU can handle some other threads. So that way, you can use the hardware threads. With that, the multiple user threads can be scheduled on a single CPU core. Yeah, these are the the same thing. Whatever like a single thread versus a single core versus a multi-core system. How the multi-threaded process will be scheduled if it is a single process, and if it is a multiple process, if it is available, then how the threads are scheduled. This is very intuitive, because if it is a single process, so the threads are scheduled in a concurrent way. Suppose a process having 4 threads, they scheduled in a this way. Like since only one processor is available, and if there are multiple cores are available, then those threads are scheduled in other way, like in a parallel way. Like a thread 1 will be scheduled here, thread 2 will be scheduled. Thread 1 and thread 2, they can run parallelly, simultaneously, and thread 2, thread 3 run can simultaneously. Whereas here and all, at any point of a time, only one thread of execution is possible. Anyway, these are very intuitive, and you can able to see here the difference between the concurrency and parallelism. This is the difference. Whereas here and all, you can say that we can say that all threads are progressing, but they are not simultaneously execution. Whereas here and all, the threads are progressing, as well as you can schedule the multiple threads where the multiple threads can run or can execute parallelly. Yeah, right. So in the context of these multi-core systems, there is one result known to be the like Amdahl's law. So this basically just provides the indicates that what will be the speed up on a multi-core systems, what will be the attained or the maximum or optimal or possible speed up that can be available on a multi-core systems and all. So for that, we know that when the if a program contains usually when you look at the program, it's not that the entire program you cannot split it into all parallel executions and all. There will be certain sequence of code that has to be run in a sequential way, and the remaining part you can make it parallel, right? So therefore, for example, here the speed up is given by using this formula 1 over s plus 1 minus s by n, where s is nothing but the serial portion. Suppose you have a execution code, total code. So in that, you can make some 25% or 30% or 10% of a code has to be executed in a sequential way. And the remaining remaining code, you can make it as a parallel and all. You can make it parallel. So that way, if you analyze the code in view of like the serializability and the parallelism, where a certain amount of code or certain portion of a code in the total can be carried out in a strict sense serial way, and the remaining code you can make it parallel. You can make it parallel. So in that case, the amount of speed up that is achieved that can be achieved with the multi-core systems will be 1 over s plus 1 minus s by n and all, where s indicates the amount of the code, the sequential code or the serial code, and the remaining 1 minus s can be the code that can be parallelizable. So that way here, for example, if the serializable code, if the serial code, the sequential code is 25%, and the remaining 75% can be make it parallel, for example. So in that case, suppose, for example, if you have a dual core system, if you run this particular program on the dual core system, you can able to achieve a speed up of 1.6 times compared to a single processor system and all. Because here n equals to 2 and is s equals to 25%. It's nothing but 1/4 of a code is the sequential code. It has to run sequentially, and the remaining code can be parallelizable. But here, however, you can parallelize here, since if it is a dual core system, that n happens to be 2. So therefore, if you substitute here, you can able to see that the speed up can be achieved will be 1.6 times. It means 1.6 times compared to a single process system. And suppose if n equals to 4, then appropriately you can able to increase the speed. If n equals to 4, then it's appropriately you can increase the 4. It may be some other order. So likewise, as n tends to infinity, for example, suppose if, for example, you have so many cores are available, or lots of processors are available in a system, for example, even in that case also, the amount of speed up is limited by the sequential code, the portion of the sequential code and all. Suppose, for example, if n tends to infinity, that means if n is sufficiently large, then this particular term 1 minus s by n, so this is negligible compared to s. So suppose if n equals to 25%, that is 1/4 of a code. So therefore, even though if you have enough number of cores are available to run the parallel portion, but still, since the serial portion, there is some amount of serial portion was there. So because of that, the speed up will be limited to the amount of the serial code, the serial portion that was there in the application program and all. So it means that even though if n tends to infinity, if s equals to 25%, then you can able to achieve a speed up of maximum 4 times compared to a single process system and all. So that's what I mean by this for the speed up with respect to the single process system in the context of multi-core systems and all. However, now it's not truly this one, because now even the cores also, as I mentioned that now we have a hardware threads are there. On a single core, you can able to run the multiple threads also. So that way you can still enhance the speed. Okay. Yeah, now we'll try to discuss about how these threads are implemented or managed and all, right? So actually here the threads, you have the like user threads and kernel threads from this. So the user threads means the threads that are introduced in the application program. So and those threads are managed at a user space, so those are known to be the user threads. And a kernel threads means the threads that are managed by the kernel, because the kernel threads means kernel is also a process, right? Kernel is an operating system, like it's a process. And if the kernel supports a multiple threads, then it can able to run, or it can able to speed up, or it can able to run parallelly also across the multiple cores and all. So here the user threads and kernel threads means, user threads means the threads that are supported in the user space, and the kernel threads means the threads that is offered by the operating system to take the advantage of the multi-core systems and so on. And so that's what user threads means. The management is done at the user level thread libraries, user level thread libraries. These thread libraries will support the user threads. That means their creation, the management, scheduling, and so on. And also there are three types of thread libraries basically, like POSIX P threads and Windows supported threads and the Java supported threads and all. And these are available both at user level and a kernel level and all. Right, and virtually mostly all existing operating systems and all, they support a multi-threaded one. It means that the operating system will run as a multi-threaded a process, and all these the operating systems, whatever mentioned over here, they support the multi-threaded. And now we'll see that how these multi-threaded models are supported, or like basically how they look like. So there are three types of models, there are implementations and all. One is a many-to-one model. We'll see that what it is, one-to-one and many-to-many model. And so this is the many-to-one model. So the many-to-one model means here there are the multiple user level threads are mapped to a single kernel thread. It means that here the kernel is not threaded. The kernel has only one thread of control. The kernel has only one thread of control, right? But it used to manage the multiple user level threads. Multiple, that means the application program have the multiple threads, but the kernel has only one thread of control. So it used to map, that means here the multiple application threads, application program, the threads present in the application program, or the multiple user level threads are mapped to a single kernel thread and all. So this is known to be the many-to-one model. And here we'll see what are the various issues that crop up here and all. That means many user level threads are mapped to single kernel thread, right? And here in this case, suppose if one user level thread is blocked, then the entire process will be blocked. Because suppose, for example, a particular thread is running, and at some point of a time of its execution, suppose it requires IO and all. So when it requires IO, it calls a system call. So that system call is nothing but it will be operated by the kernel routine. So, but the kernel will run only one execution, because the kernel has only one thread of control. So that means when the kernel take up that system call, and that system call, if that system call is a blocking system call, then the kernel thread will be blocked. Then the kernel thread will be blocked. That means the entire process will be blocked. That means even though there are multiple threads, but the whole system will be blocked, because the kernel is running on a single thread, and that particular whatever the user request or user thread, it is calling a system call which is a blocking one, that is which requires some IO, and at that time it has to wait for IO. So therefore the kernel thread will be blocked. So with that the entire whole process will be blocked, right? Whole process will be blocked. So when the whole process is blocked, then the kernel will switch to CPU to some other process and all. So therefore, even though the multiple threads may not run in parallel, and the another thing is that since even though the user process has a multiple threads, right, but there is no chance to run these multiple threads parallelly on a multi-core system. So even here, the thing is that even though I have a multi-core system is available, and if the model is many-to-one model, it means that if the application process has the multiple threads or multiple user level threads, but all these are managed by the single kernel thread. And since the kernel is with a single threaded one, so therefore, even though I have a multi-core system, so those multi-core system is not exploited by the kernel, because the kernel has only single thread of control. And finally, the kernel has to manage the CPUs, because the scheduling the threads to scheduling either threads or processes to the CPU has to be carried out by the kernel and all. So with the kernel thread, you can able to allocate, schedule the CPU to these threads or process and all. If the kernel has only one thread of control, then the kernel cannot perform the cannot utilize the these multiple cores and all. So therefore, the multiple threads may not run in parallel on a multi-core systems because only one because the kernel has only one thread of control. So therefore, it cannot manage the multiple CPUs or the multiple cores and all. So therefore, yeah, these are the characteristics of this many to one model and all. So basically, you have the multiple application threads, the user process threads are mapped to one kernel thread. If it is blocked, then a whole process is blocked, and then the CPU will be switched to the next process and all. And another thing is that even though we have multiple threads, you cannot run these multiple threads parallelly on a multi-cores because these threads are mapped to only one kernel thread or only single kernel thread. Basically, the underlying kernel will not support the threading concept. So underlying kernel is a single thread of control. So therefore, it cannot manage the multiple cores, even though it has. So this is the model, like many to one model, but but here these can be used if it is a single processor system and you have a multiple threads of control, then you can able to run these threads like in a very scheduled way based on the user thread library and all. Because suppose this particular thread is running, and then after some time you can be able to schedule this particular thread. Likewise, you can schedule these threads, or you can able to schedule the threads on this process one after another in effective way. Basically, for example, in case of suppose, for example, yeah, the idea here is that you want to run the multiple, if you want to run the process, and suppose, for example, if a process is running using these multiple threads and all, and there is a chance, otherwise, suppose if you have a process, the process is constrained by, if we have only single thread of control, then it will be blocked. It blocks whenever it requires IO and all. But here, if you cleverly manage or if you cleverly schedule these threads such a way that you can avoid the blocking to some extent. That means you can run this thread for certain amount of time, and before this thread needs IO, you can switch this thread to some other thread, and you can able to run the second thread. Likewise, based on the user thread library function, you can able to schedule these threads so that like you can postpone the blocking to some extent, or otherwise, if it is blocked, then by using some mechanism, the other threads can be scheduled instead of this one, instead of stopping the whole process and all. So anyway, these are not much used as of now. This is at earlier, actually, this threading model has been used, but right now, since the basic drawback of this is that actually you cannot use this threading model on the multi-core system. That's the basic drawback or basic limitation of this particular system and all. And these are some of the example operating systems that are supporting these particular threads. That is Solaris, Green Threads, and other things where at that time the Solaris is managed with a single thread of control operating system, and where it supports the user level threads, but the user level threads it is supporting means that is completely managed by the user thread library, the thread library that is available in the user space and all. That's nothing to do with the operating system and all. The operating system doesn't know about the threads and all. The operating system just takes an execution sequence and then it tries to run that. And if there is a blocking, then immediately the operating system will block the whole process and it switch to the next process. Yeah. The next model is that the threading model is a one-to-one model, and here it basically takes care of the drawback of the area system, the many-to-one model. The many-to-one model, the basic drawback is that we are unable to exploit the efficiency of the multi-core systems or multi-processor systems because the kernel is a single-threaded process and all. Whereas here the one-to-one model where each user level thread maps to a kernel level thread. That means whenever the user level thread is created, the corresponding kernel level thread is created, and then this particular user level thread is mapped to the kernel level thread, so that the concurrency and as well as the parallelism is also can be taken care of over here. Whereas it is more concurrency than the many to one, obvious, because in case of many to one model, it supports only concurrency. It's not supports any parallelism and all, but here it supports both concurrency as well as parallelism. So with that, it is more concurrent compared to the many to one model and all. And the number of threads per process sometimes restricted due to the overhead. Yeah, what it means here is that suppose the process keep on creating the threads, means in this particular approach, where whenever the user process is creating a thread, it means the kernel process also create a thread, and then it has to bind or it has to map the newly created user process thread to the kernel thread and all. So as the number of user threads are increasing, it means that proportionately or equivalently the kernel threads also has to be increased. But the managing this the several kernel threads in the operating system and all, it's very hectic because each kernel level thread has to maintain its control information, its status, and everything and all. So therefore, at certain point of a time, managing more number of kernel threads is also very difficult. It also indirectly it hampers the performance of the system and all, because it needs to look up, it needs to take care about a lot of like maintaining the control information and all. So that way it puts sometimes a restriction on the number of user level threads and all, because as per this model, so whenever the user level thread is created, the corresponding kernel level thread has to be created, and then it is to be binded, it has to be mapped to that. So as the number of user level threads are increases, then the kernel also has to increase the threads to support the user level threads. So with that, the overhead will be increased, and it sometimes affects the performance, the overall performance of the system and all. So this was the idea of the one-to-one model, and it is a reasonably good system which takes care about the parallelism and the concurrency and all. And all these operating systems will support, the recent operating systems will support this one-to-one model and all. Windows, Linux, and the Solaris 9 and later systems and all, they support the multi-threading with this model, like one-to-one model and all. So the next model is the many-to-many model, and here the idea here is that in case of one-to-one model, the problem or the difficulty what we observed is that as the number of user level threads are increasing, then the kernel will be overloaded, because so many threads the kernel has to maintain. So it needs a lot of the additional overhead. So with that, it hampers the performance and all. So that's why here in the many-to-many model here, there are multiple user level threads, and the kernel also supports the multiple kernel level threads, and the number of kernel level threads will be less than or sometimes maybe equal less than the number of user level threads and all. That means the kernel will support some fixed number of threads, whatever it can able to accommodate, and whatever the number of user level threads and all, so they will be mapped to these many limited number of kernel level threads and all. It is kind of a multiplexing and all. So there may be the many user level threads, but the number of kernel level threads are fixed, and all these user level threads are mapped to these fixed number of kernel level threads in the form of some kind of multiplexing. And also, so with that, actually, it takes care about the overloading of a kernel or overhead of a kernel can be taken care to some extent, because here the kernel maintains the limited number of threads. So with that, it can support it takes care about the overhead also. It will not burden too much about maintaining these multiple threads and all. And yeah, that's what it is. So allows the many user level threads to be mapped onto the many kernel threads, allows the operating system to create a sufficient number of kernel level threads, and as I mentioned here, and so these systems and all support this particular many-to-many model. And this is another one. This is a version of the many-to-many model, known to be the hybrid level model or two-level model and all, where it supports both. That means you can see that this is the many-to-many model, and as well it also supports for certain user threads. It provides separate mapping to the kernel level threads and all. It's a normal the many-to-many model. There is no restriction. That means there are multiple user level threads are there. Somehow these are multiplexed to the fixed number of kernel level threads. But there are certain applications maybe. So in those applications, there are some specific threads that need to be attended by the thread, by a kernel, that need to be give a lot of support or has to be attended by the has to be executed properly by giving proper attention and all. So in that case, you can identify those user level threads, and they can be separately bind to or map to a kernel thread, specific kernel threads and all. So this is known to be two-level model, which supports to like many-to-many and the one-to-one mapping. But this one-to-one mapping is for a limited sense, only for a specific threads. Only it will support the one-to-one mapping. For the remaining case, it supports the many-to-many model and all. So these are the different ways where the user level and kernel level threads are interacting or like mapped. And then coming to the thread libraries are nothing but actually these are the library functions which supports the threading. The threading means basically the creation of a threads, then the managing the threads and so on. Because the creation of a threads means based on the nature of application, you need to create a thread. That means you need to identify the blocks of a code where you can able to run parallelly or where you can able to run those blocks independently. Like you can exploit the data parallelism and task parallelism and so on. So for that, actually you need to identify that and you need to create a threads appropriately. And afterwards managing the threads, as I mentioned that since these threads are the separate execution sequences, sometimes there will be some data dependencies will be there across the threads and all. So at that time you need to manage properly. You need to manage the threads properly. That means you need to wait a particular thread to until a completion of some other threads and all. So that way all these things will be taken care by the library function supported, known to be thread library function. And supported with the API, that is application programming interface. This we know that because this API we come across when we are dealing. Suppose the user program needs to like execute some system calls or perform certain job with respect to operating system, then it calls the system calls by using these APIs and all. So the same way here also, in view of threading also, there is some separate thread functions, thread library functions. Through API, you can able to manage the threads and all. Right. So here these thread libraries, they can be here. These thread libraries may present in the user space as well as in the kernel space also, in the user space and kernel space. And as we have seen in the model, like many-to-one model, where you have a thread library that is available only in the user space, because it's a many-to-one means the kernel has only single thread of control. That means the kernel has only single execution sequence. So therefore, it doesn't matter. It doesn't need any thread-related functions and all. So therefore, in case of many-to-one model, where the thread library will be entirely present in the user space only, in the user space. And whereas other models like one-to-one or many-to-many models or two-level models and all, where you have a libraries, thread libraries, both available in the user space as well as in the kernel space also. Right. And coming to the one of these thread libraries, as I mentioned, like there are three the operating system support basically three popular the thread libraries. One is the P threads supported by the POSIX and all, and then the Windows and Java threads. And here this provides both the user level and kernel level, these P threads and all. And here this P thread provides the API. And this API, these thread library functions used to support the thread creation and synchronization. So here creation and synchronization, and basically here these APIs will provide the specification. Means it just provide that the overall the objective or like the overall like what will be the input, what will be the output. So that kind of a specification is provided by the API and all, and it is up to the developer to support that. That means that depending upon the developer, you can able to support that, but it has to satisfy the specifications provided by the API and all. That means suppose you have a thread and all. So what are the properties? What are the characteristics that thread function supposed to be performed? So that is the specification, and the implementation will be that is up to the user or the library, where the library function will implement that to support this particular specification and all. And here, as I mentioned, the thread creation and the synchronization. So we'll see that what is the creation and synchronization. Let me see. Yeah, in the context, suppose for example, you can have these threads of different types, like synchronous threads and asynchronous threads and all. So in the concept of synchronous threads means, suppose a thread creates a thread, the other thread, suppose a new thread is created by some parent thread, for example, a child thread is created. And in case of synchronous threading, the idea was that the parent thread or a thread will create some threads, some child threads, and afterward this thread will not perform any job. It's just waiting for completion of those threads, those child threads and all. And upon completion of those child threads functionality, or those child threads are exit from their work, then it takes the input from that or whatever, then this parent thread starts executing and all. This is just like the way what we discussed in the relation between a process and child process, and a parent and child process and all. In case of certain fashion, certain execution, where a parent creates a child, then afterward the child will execute, and upon the child termination, then the parent starts execution and all. So at that time, the parent, after creating a child, just wait till the completion of a child process. The same way here also, in case of asynchronous way of thread implementation, synchronous way of thread implementation, a parent thread or a thread will create certain threads, and the created threads are known to be the child threads, and the created one is known to be a parent thread. And a parent thread, after creating the threads, child threads, then it will not perform any job, just waiting for completion of those threads. And then upon completion of those threads, then this particular parent thread starts execution. Like for example, if you take an example of that summation, computing the summation using a data parallelism, where in that case, for example, you can create, the parent thread can create some 3 or 4 threads, and it will split the array of numbers into 3 or 4 partitions, and then it will pass those sub-arrays into those thread to the child threads, and the child threads will execute their partial sums. And upon the completion of the partial sums, then the child threads will be terminated. Then the parent thread will resume the execution. It takes the partial sums, and it will sum up those partial sums, and it will display the overall sum. So this kind of execution is known to be the synchronous way of thread handling. In case of asynchronous way of thread handling, it's different. Asynchronous way of thread handling, a thread will create some child threads, and then both the child thread and the parent thread will execute simultaneously, will execute as per the schedules and all. It means that there is no relation between the relation means there is no like the parent and child thread, they will not be synchronized. That means the parent thread will create a child thread, and after that the parent thread will start its execution, and the child threads also will start its execution and all. That's known to be the asynchronous way of the threading and all. And so in that case, actually, we need to have this kind of synchronization. All these things are required. You need to have appropriate, the thread library functions are required. Okay, yeah, right. So yeah, these things we have discussed here. And yeah, if you look at here, this example, like how the threads are created and how the threads are like managed or synchronized. And anyway, this is just for this is the initial part, like it's a thread identifier, and the set defining the set of attributes, thread attributes. Set of thread attributes means each thread has some thread ID, and each thread has some scheduler priorities and all. So likewise, those are known to be the thread attributes and all. So if you want to create a thread, it should have some thread ID is required, some thread attributes are required. And then if you look at here, like first of all, before creating a thread, you need to set the attributes of a thread, what is need to be created and all. So therefore here, by using this particular function call, you can able to set the attributes of a thread. Suppose a particular thread, if you want to create, so before that, we need to know about actually what is the functionality of that particular thread. And accordingly, you need to set some attributes to that particular thread. Suppose that thread has to be done in a very prioritized manner and all, then it has to be given higher priority. So likewise, the attributes of a thread has to be set here before a thread has to be created. So by using this particular function, the pthread attribute initialization. So with that, you can able to initialize the attributes of the a thread to be created and all. And once the attributes are set, using this particular function call. Then afterwards, you can able to create a thread. For that, this is the thread function, like a pthread create. With that, you can able to create a new thread, and then you need to. This is the thread ID. That means it returns this particular thread ID, and these are the attributes that you are passing. And this runner is nothing but actually the first address or the address of the execution where it starts, address of this thread where it starts, because you have a process, and in that actually each thread will start from a particular point of from a particular instruction to a particular instruction. It has to be executed and all. So this runner is nothing but actually this is a particular function in the main program and all. And now we are creating a thread to run this particular function, specific function and all. So this is nothing but actually the function name. It's nothing but actually the starting address of the thread where the thread execution will start. Right. So these are the various arguments where we need to be passed for creating a thread and all. Thread ID, attributes, and the first address where the execution has to be start. And this is anyway related to the arguments and all. Then afterwards, here, this is the case where the simultaneous threading. After creating a thread, then the parent thread will wait. The parent thread will wait. That means pthread join. This particular function is nothing but this thread. That means the parent thread will wait for this particular thread ID to complete. That means now whatever the thread ID, whatever the thread you are creating, so that particular thread has to be completed. Because when you create a thread and all, so the parent ID will come to know about the thread ID, whatever it's created. And then afterwards, in case of simultaneous, in case of synchronous threading, after creating a child thread, the parent thread will wait till the child until the child thread completes. So, and then the child thread is created. Now the child thread will starts execution starting from this particular function, and upon completion, then it returns the TID. So then till that point, this particular thread, the parent thread, will wait. And then upon the completion of that particular thread, then this particular thread starts its execution. Then it's print the sum and all. So here, what is this? When you create this thread, a new thread will be created, and this new thread starts execution from this particular function called runner. So this is your runner function. This is your runner function, and this function is simply to compute the sum of some numbers and all. So this is a function, and then this function will be executed. That means whenever you are creating a thread, that thread will be created, and then it starts execution from this particular function called runner and all. And this is execution of this one. At the end of this function, you have the thread exit is there. Pthread exit. It means that this thread will be terminated. This thread will be completed and it will be exited. And upon this exited, then this parent thread starts execution and it prints the sum. So that way, so here, if you look at here, this particular related to this pthread, for initialization of attributes, you have the attribute initiation thread function. And then for creation of a thread, pthread create is there. And for waiting purpose, you have a pthread join function is there. And yeah, likewise, and here for exiting, exit from the thread, you have a pthread exit 0 is there. So likewise, these are the various thread functions which are supported by the thread libraries and all. Okay, and sometimes, suppose you are creating multiple threads. Suppose the previous example is just to illustrate that only one thread is created, and upon completion, then the parent thread starts execution. Suppose in general, mostly you have multiple threads you are creating. So here in this case, suppose you are creating 10 threads and all. And then the parent process, upon creating these 10 threads, it has to wait for completion of all the threads. So it just wait for these threads using the for loop. It just wait for completion of all these threads. Once all these threads completion is done, then it starts executing under. So likewise, you can able to manage the multiple threads in case of the synchronous way of execution of the multi-threaded process and all. Yeah, the next one is the same thing. Whatever the earlier one, the illustration is for using a pthreads, and now this is for Windows environment. In the Windows environment, how these thread, what are the various thread functions are there, and how these thread functions used to for managing the threads. That means for creating a thread, and then for waiting for a thread, and for terminating the thread and all. So these are the various functions here is given. You can go through that. It's almost follows similar to the P threads only, but the naming conventions are different. Like for create thread, you have create thread and it returns the thread handle and all. The returns the thread handle is nothing but, whereas earlier and all, it's the PID will be there, and with the PID you will come to the parent thread will come to know that what is the thread ID of that. And here and all, it just returns the thread ID. It returns the ID. So that's the thread handle and all. And for creating a thread and all, it requires certain attributes. Here they are mentioned here and all. What is the stack size? What is the thread function? Where it starts and all? What are the parameters to be passed to the thread function? So all these, what are the flags? So all these things are like you can pass for creating a thread and all. And again, same thing for in case of synchronous way of handling, where after creating a thread, then the parent thread will wait for a particular thread, whatever the thread that is created. So thread handle indicates whatever the thread it is created, and then it is just waiting for completion of this thread handle and all. And upon waiting this one, then it closes the handle, and this is the way it can do that. It's just similar to the one whatever we discussed. Yeah, the next thing what we are going to discuss here is that the implicit threading. So, so far, whatever we discussed is that you have threads where the application programmer can introduce the threads when he's writing a code or when he's doing a programming and all. And as we have seen that because the application programmer has to look into the different aspects of that, he has to identify that what are the different tasks and whether the tasks are independent or not. If they are not independent, how to provide the synchronization among them. So all these things will be very hectic, and it will be pressure for the application programmer to perform job and all. And it also very difficult to check the correctness of this multi-threaded process and all. So therefore, the concept of implicit threading is nothing but it reduces the burden on the application programmer or the system programmer and all. So because reduce the burden, so in the form of like implicit threading means in the program itself automatically the threads are created based on the nature of the code, and then the threads are managed automatically. So here you will see that that's what the concept of implicit threading. The implicit threading means creation and management of threads is done by the compiler and the runtime libraries rather than the programmers and all. That means the programmers will give at a very broader level, they can able to specify that actually which blocks of a code can be parallelizable and which blocks of a code can be where the threads can be incorporated. So that way at very higher level, they can able to provide the directives to the compiler and all. Then at the time of compilation, then the compiler, by looking at those directives and all, it can able to introduce the threads and all, introduce the threads and manage the threads also. So that's what mean by the implicit threading. It means that it in a kind of semi-automatic way of introducing and managing the threads by the system and all. For that, it makes use of the compilers and the runtime libraries and all, right? And so there are three different methods we'll try to look into it. One is the thread pools and the OpenMP and a grand central dispatch and all. So these are the three different ways or methods can be used to exploit the implicit threading, or can be used to introduce the implicit threading and all. And also there are other methods also there. In case of Microsoft, it supports the thread building blocks and all. So with that also it can able to introduce the threading in a semi-automatic way and all. So we'll see that one after another. In case of thread pools, so here the idea of thread pools is that it's basically used, for example, in case of like as I mentioned, client server paradigm. Suppose you have a web server is there, and there will be a lot of requests used to arrive or used to be serviced by the web server and all. And in that case, there are lots of requests used to come in a very frequent way. So whenever the request come, a thread has to be created and it has to be assigned to the request and it has to be responded. So the creation of a threads will take time, will take some reasonable amount of time. Whenever the request arrive and you need to create a thread, and then you need to assign the thread to the particular request, and then the thread will take care of that. And again, the thread will be terminated back. And again, new request arrives, you have to create a thread. So what I mean to say is that for certain applications and all, you need to have a lot of requests used to be there, or you need to have frequent creation of a threading, threads are required and all. So in that case, the one idea here is that instead of creating a thread as and when the request is arrived, instead you create a thread at the beginning itself. Whenever the process initiation taking place, or process at the beginning or at the initiation time itself, you create a pool of threads. You create a pool of thread or create a certain finite number of threads, and those threads are waiting in a pool. That means the threads are ready, they are already created, they are ready, and whenever the request arrives from a client, then one of the thread from the pool is picked up, and then that request will be passed on to the particular thread, and the thread will take care of that request. Whatever the request, based on that, it sends a response back, and upon completion of the task, then again the thread will come back and join in the pool. So that way, the thread creation time will be reduced, and with that, it will be a bit faster compared to each time creating a thread as and when the request has arrived and all. And another thing is that with by using these thread pools, you can able to restrict the number of threads. Otherwise, if there is no, if that is not the case, whenever the request arrives, and if the thread has to be created, if the new thread is created, in that case, suppose if there is a demand at a particular time, or at a particular instance of time, if there are a lot of requests have arrives in a very small amount of time, so in that case, as per the process, as per the the protocol, new threads are created for every request and all. So at certain point of a time, the number of threads that are created will be very huge, very large in number. At that time, you have the resource crunch will be there, because each thread, it requires certain resources, even though they share the process resources to a larger extent. But to survive each thread or to execute each thread, it requires its own stack, it requires its own register set, and it requires some memory to keep your local memory, local data, and so on. So therefore, if the number of threads are created beyond a particular limit and all, then you can have the starvation of resources, or the resources will be exhausted and all, and that will indirectly reflected in the performance and all. So therefore, the thread pools is one of the solution where at the time of at the creation of a process itself, you will create a finite number of threads, and then those threads will manage the request sender. For example, when the request arrives and at that particular point of a time there is no thread is available in the pool, then the request has to be wait till one of the thread is available. One of the thread will be available. That means one of the thread completes its job and again come back to the pool. At that time, that thread will be given the new request and all. So that way, one way is that actually you can able to control, you can able to avoid the situation of exhausting the resources can be done by using the thread pools and all. And then the number of threads, the pool size, how to control the pool size, who decide the pool size, that depends upon both the system resources and the number of requests also. That means the underlying system server, how many cores it has, and what is the physical memory that is available to the system and all, and the number of requests also. So based on these three things, you can able to decide the pool size approximately, and then initially you create that many number of threads. And the sophisticated systems and all pool architectures, they vary the pool size dynamically and all. That means that depending upon the demand, the request, the pool size will be varied and all. That means by using some prediction strategies and all. So at certain point of a time where you require the pool size to maybe less and the pool size to be more and all. So accordingly, you can able to vary the pool size dynamically based on certain statistics and certain modeling criteria and all. Right. So this is about the pools, thread pools and all. So this is basically used to reduce the time for creation of a threads for certain applications, and also that it also takes care about the number of threads that can be manageable and all. Like otherwise, if there is no limit on that, if the threads keep on creation, then you can have the resources will be exhausted, and it negatively affect the overall performance of the system and all. So this is about the thread pools. And there is another way of introducing implicit threading is the OpenMP. It's nothing open multi-processor system and multiple processing. And here in this case, the idea here is that the user, that means the system will identify the parallel regions in the code known to be blocks, And these regions will be like the application developer will introduce the compiler directives. That means wherever the, for example, simple thing, wherever the for loop is there, it means that whatever the set of instructions, whatever the instructions that are there within the for loop, they have to be executed multiple iterations and all. So that way, wherever the code is parallelizable or wherever the parallel sections of code or independent sections of code is there, then instead of writing the detailed code, creation of a threads, everything by the application programmer and all, the application programmer will just inform some, introduce, insert some compiler directives, something like that, like the hash, pragma, open, OMP parallel. It means that after this, whatever the code is there, it can be parallelizable and all. So that way here the user, or you can say the application programmer, will introduce the compiler directives in the code. So with that, whenever at the time of compilation, the compiler, whenever it encounters these directives, it understands that the following code, following block of code can be parallelizable. So it immediately create the number of threads, as many number of core. For example, if a quad core processor is available, then immediately 4 threads are created. And then whatever the data, whatever the iterations are there, these iterations will be spread across these 4 cores and it can be run parallel and all. So that is the way you can able to like introduce the threads, manage the threads in a very, in a more or less in automatic way. But for this, the application programmer has to introduce the compiler directives in the code and all. So it is much easier compared to like writing the whole the thread manage whole thread functions and all with by inserting without inserting thread functions. If you just inserting the compiler directives, then it will be the system will takes care of creating a thread and managing the threads and all. So this is about the OpenMP, and you can able to see that. For example, this is the code. For example, just matrix. You are adding 2 arrays and then pushing into some other array and all that you have to do for n iterations, right? So that you can able to do that by spreading the code in the across the multiple cores, and you can do that. And similarly, the grand central dispatch. This is also the idea is similar to the OpenMP here also, but here the application programmer again will identify the sections of a code which is parallelizable and which is not parallelizable. So that way he will identify the code and the form of these particular directives, like this one, the caret followed by the 2 curly braces. So this indicates that whatever the code that was there within these 2 curly braces in front of this caret symbol, that is can be parallelizable and all. So that way the application programmer will introduce these kind of directives. And at the time of compilation, we will come to know that, yeah, these are the portions of a code where you can able to be parallelizable, and this is the code where it can be independent. So that way you can come to know about the different blocks of code. That means from the code, we'll try to define or try to divide the code into multiple blocks. And those blocks can be, some of the blocks are the serial blocks and some of the blocks are the parallel blocks. So therefore, to maintain this or to perform the execution of this one, we'll use the different types of dispatch queues. For serial blocks, they will be dispatched to the serial queues, and for a parallel blocks, they will be kept in a queue known to be like a parallel dispatch queue, and which can able to run concurrently. In case of serial queue, the blocks are pushed into the serial queue, and then here a block is fetched from the serial queue in a first come first order. And then that entire block has to be executed. And upon completion of that block, only the next block will be fetched from the serial queue. Whereas in case of concurrent queues, the idea is that because here in these queues, the blocks are parallelizable. So therefore, here we'll take multiple blocks at a time, and those blocks will be like scheduled to the multiple processes, and it will be run parallelly. So that way you can have these two types of dispatch queues will be there. The system will maintain the 2 types of dispatch queues. One is the serial and concurrent. Serial will be the serial portions of a code. Those blocks will be placed in the serial queue, and whereas the parallelizable code can be placed into these parallel dispatch queue and all. And the blocks will be fetched from that, and it will be scheduled to the multiple cores accordingly. So this is there are some other the other parts we can continue in the next class and all. So since now it's 11:35, so we'll stop the lecture at this point of time. And now you may go to the your yeah, you can just go to the Teams and you can wait for this quiz. Hmm? No, I thought today I'll somehow I can complete these threads so that the next class will start the CPU scheduling and all. You can complete that in one class, but anyway, so we'll try to see that. We'll continue this in the next class and all. Yeah. Yeah, I'll stop recording here.